So, chapter 10, acids, bases, and salts. This is the last chapter in the course, and it's along with chapter 9 will be covered in exam 4, which is scheduled for May 3rd. And I believe that's during the final grades due. That's during final exam week. And that's all we'll be doing. You can either come here in person, or if you request, I can enable the exam in Brightspace for you to take from home. But I'm going to be here regardless. Okay, chapter 10, acids, bases, and salts. All right, we got a lot of subtopics to cover here. First, we're going to define what an acid and a base is. And then we're going to introduce different types of acids and what we mean by acid strength, base strength. We're going to introduce equilibrium into this concept of acids and bases. And then we're going to neutralize an acid with a base, which we've already done in the lab, pretty sure. Le Chatelier. No, we're going to do that in our last lab. And then we're going to talk about water and how water behaves. And then introduce the concept of pH. I may get that far. If I don't, then we'll pick it up next week. And then we'll talk about buffers and some other details. All right. So, acid-base theory. We're going to take this in chronological order. There was a chemist who was from Sweden. His name was Svante Arrhenius, late 19th century. And many scientists in Europe, particularly in Europe, were investigating acids and bases. And they needed an idea as to what constitutes an acid and base. They knew the qualitative expressions of acids and bases. Some of those had come out of the Middle Ages from the alchemists, right? Alchemists used strong mineral acids to facilitate certain reactions, right? They already knew about hydrochloric acid. They knew about nitric acid. They knew about sulfuric acid already. And they knew that they all exhibited certain common characteristics. But what Arrhenius tried to do was describe what those characteristics were based upon. Why do they behave the same way? And what he came up with, the Arrhenius definition. The Arrhenius definition of an acid is any species that has a dissociable, or an ionizable, I should say, an ionizable hydrogen in it that will produce this separate hydrogen and what's left over. Right? And when it does that, it leaves its electrons, right? There's a bond here. It leaves the electrons behind and it exits only as a proton, right? Hydrogen with no electron is a proton. Most of them anyway. Okay, that's an acid. And Arrhenius also said that a base is a compound that has a hydroxyl polyatomic ion in the molecule and it dissociates. There. So what he's saying is that the acid reaction characteristics are based upon that species right there. And for a base, its reaction characteristics are based upon this species right here. Okay? And for a great many compounds, this is perfectly adequate definition. It covers most of acids and bases. Our example here is nitric acid and sodium hydroxide. Okay. Now there's a difference in the way that these two reactions proceed. This is an ionic association right there. That's positive, that's negative already in the molecule. This one, however, is covalent bond. So we have to ionize this molecule. We have to separate the charges. Ionization is the process. Where this one is, you just need to separate the pre-existing ions. We call this dissociation. Okay? It's a subtle distinction, but significant at the molecular level anyway. And there's an artist's rendition of what happens. Okay, so there's the Arrhenius definition of an acid and a base. Here's the problem. If the problem is not with the acid, the problem was with the base. If the behavior of a base is dependent upon hydroxyls in solution, right, we have to put them in aqueous solution. Right, aqueous all across. Then how do you get a basic solution with a molecule that does not have a hydroxyl in its nature, in its formula? For example, ammonia. Ammonia, when we dissolve it in water, produces hydroxyls. That's a fact. Arrhenius definition won't accommodate that molecule. So we need another definition that will. And that's where Lowry and Bronsted come in. I want to spell it correctly. Lowry-Bronsted definition. The Lowry-Bronsted definition takes into account the Arrhenius. It incorporates all the Arrhenius molecules that could be acid or base, and then incorporates into that those that don't fit Arrhenius and includes them. And they do it by focusing upon the hydrogens. The hydrogen transfer is the focus, not the hydroxyls. So what they say is, when you put the ammonia molecule in water, you transfer a proton or a hydrogen ion from the water molecule to the ammonia molecule, and now you get the polyatomic ammonium ion plus the hydroxyl, right? Look at this. That's water, right? If you take that one out, what do you got left? You got OH minus. Okay, so Bronsted-Lowry focuses on hydrogen transfer, hydrogen ion transfer. So what they're saying is that the acid donates a proton and the base accepts a proton. Okay, that's their definition. And it works for all aqueous acids and bases. All right. Now, we're going to go with mostly Bronsted and Lowry's definition, but sometimes Arrhenius works also. It's just a matter of convenience, actually. All right, so when we have an acid that goes into solution, and our example here is hydrofluoric acid. It reacts with water molecule. And it actually sets up an equilibrium. So when we wrote it like this before, HF yields hydrogen ions plus fluoride ions. That's an oversimplification and a useful one. I mean, if you have to do calculations, then you'll get the same results with this one or the one I'm going to show you next. But this is actual chemistry. This is what happens in aqueous solution. You transfer a proton here to here, and you get the fluoride ion plus this new polyatomic ion. This is the hydronium ion. Now, by definition, Bronsted and Lowry says this is an acid. And water becomes a base. Donates the proton, accepts the proton. All right? So when we come to this side, now water has an extra proton that it can donate. So it is now what we call the conjugate acid. It's the conjugate acid of that base. And this is the conjugate base of that acid. Okay? Okay. Now, when the question arises, do you have a conjugate acid-base pair? What they're referencing here is, if we say this is an acid, what would be its conjugate base? Characteristics. Second. Hello? Hello?
Yes, hello, good morning. Am I speaking with David?
Yes, I'm teaching a class right now. I can't talk.
Okay.
So there are two characteristics of the conjugate acid-base pair that are required, essential. One is you have a hydrogen here that can ionize. And when you lose that hydrogen from this acid, it produces this part of the molecule. Notice that this part is the same as that part without the charge. And this one is absent one proton, one hydrogen. So this is an acid-base pair. If we did something like this, if we said, is this an acid-base pair? HF and OF minus, right? That would not be an acid-base pair, because this is different from that. Even though we supposedly lost one proton, this part of the molecule is not the same as that part. So that would not be an acid-base pair. Okay, for this reaction, the acid-base pair would be HF and F minus, which would be B. Okay? Now let's talk about water. Water is the solvent. It's the major component of the solution. When we put an acid or a base into solution, the solvent is water. But water has an interesting reaction of its own. It's called amphiprotic or amphoteric. Amphi means both. What that means is, if you have pure water, then it can react not with itself, but with another water molecule. One of them can act as an acid and one can act as a base. You know, take your pick. If this proton transfers over here, that means this one's the acid and this one's the base. What does that produce? Well, that one lost, so it's now hydroxyl, and that one gained, it's hydronium. All right. Another way to write this in abbreviated form is just take one water molecule and produces a hydrogen ion plus a hydroxyl ion. That's another way to write it. It's not chemically accurate. This is the chemistry. But for calculation purposes, this is perfectly all right. Okay. So this is always happening in aqueous solution. No matter what else is going on, this happens. And if we write an equilibrium expression for this, right, it would be K would equal, this is a pure liquid, right? These are aqueous. So that one does not enter, right? These are in the numerator, right? Hydrogen ion concentration, hydroxyl ion concentration, and nothing in the denominator because it's a pure liquid, okay? This is given a special subscript, Kw. And at 25 degrees C, this Kw is equal to 1 times 10 to the minus 14. All right. Something I didn't mention earlier in equilibrium discussion. We never write the units of measure for a K. The reason for that is practical. Right? With all the powers that can go in and all the different numbers of reactants and products that you can have, the units of measure for the K would be sky's the limit. Right? It's just too unwieldy. So we just have to be extra careful with how we construct our Ks and how we calculate them. And we have to know whether they're in molarity to begin with or in atmospheres for partial pressure. Okay, we'll come back to this one in a few minutes. Definitions. What's a monoprotic acid? A monoprotic acid has one proton right here. All right, it can only give up one proton. Example. Acetic acid, right? It has 3 protons there and 1 proton there, 1 hydrogen ion here. These 3 will not ionize, but that one will. And sometimes we write it this way. CH3 for that 1 carbon in these 3, and then C O O H. Sometimes we write it that way. And this gives you more information about the structure, right? Those hydrogens are fixed. They do not move under most circumstances. But this one, that's the acidic proton. That's the one that ionizes. That's a monoprotic acid. A diprotic acid has the potential to release 2 protons or 2 hydrogen ions. Sulfuric acid, right, in aqueous solution. Right? If it loses 1 proton, then it will produce this polyatomic ion. Right? Hydrogen sulfate ion. So the acid-base pair would be H2SO4 and HSO4 minus. But this one can also lose a proton. And produce the sulfate. Okay? So you get 2 possible ionizations here. One here, and each one, Ka, has an equilibrium constant. Right? And then there are triprotic or polyprotics. Good example of a triprotic is phosphoric acid. Okay. It can lose 3 protons as it ionizes. It can go through 1, 2, and 3. It'll have 3 K values, 1 for each proton. And then polyprotic is any number 2 or greater. Some organic molecules are polyprotic. But most, I don't know of any inorganics that are more than 3. Okay. More definitions. In chemical terms, what do we mean by strong? A strong acid. When we're talking about a strong acid, we're essentially saying that the acid, example, hydrochloric acid, completely dissociates, completely ionizes into hydrogen and chloride ion. Now, it's only one way. Or you could also say the equilibrium position lies far to the right. We could do it this way. So like this. And then a little bitty one that way. Strong means it's essentially complete to the right. Here are examples of strong acids, right? All of the halogens except the fluoride are strong. Hydrochloric acid, hydrobromic acid, hydroiodic acid, polyatomics, nitric acid, chloric acid, perchloric acid, sulfuric acid. Those are all strong also. Now, when we talk about strength for polyprotic acids, the strong characteristic of this reaction, say for sulfuric acid, is only for the first proton. Once you get rid of 1 proton, what do you have left over? Right? That's what you got left. And removing a proton from a negative ion is positive, separating a positive from a negative is much, much more difficult. It's purely based on Coulombic attraction. Weak acids, on the other hand, the equilibrium falls far to the left. So for acetic acid, it's going to be like this and like that. Plus the acetate ion. Okay? That's a weak acid. And it's an artist's attempt to explain. All right. Strong bases include all of the alkali metal hydroxides: lithium, sodium, potassium, rubidium, cesium hydroxides. They're all strong. They completely dissociate. The alkaline earths are only strong for calcium, strontium, and barium, but there's a caveat. The hydroxides are generally insoluble. They're very sparingly soluble in aqueous solution. So when we talk about strong bases in those terms, the molecules that manage to get into solution are completely dissociated. But there are a lot of them that don't. How about strong acid? Which one would express? Well, the arrow going to the right is bigger than the one to the left. So that would be a strong acid. Now, when we're discussing equilibrium with acids in solution, we can write an equilibrium expression, in this case, the Ka is the acid dissociation constant, equilibrium constant. And it's written the same way as always, right? You can write it as the chemical reaction here, and you leave water out because it's a pure liquid. And the hydronium goes in there. Or you can say this: products and reactants. Like that. That would give you the same results as this expression. Sometimes we express how completely an acid dissociates, or ionizes, excuse me, how far it ionizes based upon percent acid ionization. They say dissociation here, but that's not right. It should be ionization. And all we do is we take the equilibrium concentration of A minus divided by the equilibrium concentration of the undissociated acid times 100. And that gives us our acid ionization constant, or value, excuse me. It's not a constant, it's a value. It will change with the position of the equilibrium. All right. We can say this much. If this value increases, this is percent ionization. If this increases, we can say that this is a stronger acid. It gets stronger as this value increases. The acid strength also increases as Ka increases, right? Because that means there's more of this and less of that. So both are true. As this increases, as the strength of the acid increases, that will increase, that will increase. All right. We can do a base. That's not right. Base ionization. Hold on a second. Let's see if I got my terms right. Ionization. Acids ionize, bases dissociate. Okay. So when we get down to this position down here, oops, sorry, went too far. Here we go. It should be base dissociation, not base ionization. And there's an equilibrium for that one also. So when we say a base, any base plus water is an equilibrium with a transfer of a proton to that base, and we leave the hydroxyl behind. That gives it the base character. And we can write the Kb for this one also. It will be this species and hydroxyl divided by this species concentration. Now this is generic. If the base is already charged, then you have to calculate what happens, right? If you add a positive and it's already a positive, it becomes more positive. If it's negative and you add a positive, then decreases the value. Okay. So when we take actually, we're talking about salts here, and we're not in chemical terms, we don't describe a salt as sodium chloride. That's table salt. A salt in chemical terms is the result of this reaction. If you have an acid plus a base, you get water, right? Hydroxyl and hydrogen, and you get Ba. That's a salt. In chemical terms, the salt is one of the products of an acid-base reaction. Right? Acid, base, water, salt. And now the salt, it could be insoluble. It could precipitate, right? If it's solid, it precipitates. Most of them don't. Most of them remain in solution as the individual ions. All right. Here's our neutralization reaction that I just described here. And these are examples. Hydrochloric acid plus potassium hydroxide makes water plus potassium chloride salt. That's one example. Acid, base, salt, and water. Okay. So here's where I left this one up here, right here. Oops, like that. Because I was pretty sure another slide was coming along. And that's an artist's rendition of what happens between two water molecules. Oh no, I'm sorry. What happens with an acid and a base is that the acid actually produces hydronium ions. And the hydronium ions react with the hydroxide ions to produce two waters. So it's actually this direction. For an acid-base reaction, you have acid, base, goes this way and makes water. That's the outcome of an acid-base reaction. And I don't know of any acid-base reactions that are neutral, heat, or endothermic. They're all exothermic. Now, self-ionization is what we're describing here, where you get water reacting with itself or its neighbor and making hydroxide and hydroniums. So I mentioned earlier, I said it was 25 degrees C. Actually, it's 24 degrees. So it's a degree less than standard temperature. The kW for water is 1 times 10 to the minus 14. And at that temperature, no matter what else we do, whether we add hydrogen, acid or base, once we know what the hydrogen ion concentration and the hydroxyl ion concentration are, multiply their concentrations together, they must always be 10 to the minus 14 at 24 degrees Celsius. No matter what else we do. So when we talk about let's see, let me make some room here. Say we have, let's say kW equals 1 times 10 to the minus 14, and that's equal to this product. So in pure water, we have this situation. So if one molecule of water dissociates, right, this is abbreviated form, dissociates, how much do you have here? Well, for every one of these, you get one of those, but you also get one of these. So for pure water, the concentration of hydrogen and hydroxide are exactly the same. And that's the first possibility in this illustration, right? When the hydrogen ion and the hydroxyl ions are equal, you have a neutral solution. If, on the other hand, you increase the concentration of this one, right? It has to be 14. Say we increase the concentration here to 10 to the minus 2 molar. Right? If that's equal to 10 to the minus 14, what does this one have to be? This one must be 10 to the minus 12 molar. All right? That will be an acidic solution. If we reversed it, right, make this one 10 to the minus 2 and this one 12, that would be a basic solution where the hydroxides dominate. And before, the hydrogen ions would dominate. Those are the three possibilities. Neutral, where they're equal. And by the way, if this is 10 to the minus 14, what do these have to be? If they're equal, they must be in pure water. 10 to the minus 7th molar, each one. But if they are equal, that's neutral. Right? If this one is dominant, it's acidic. If this one is dominant, then it's basic. All right. So let's do some calculations. Okay. Calculate the hydronium or the hydrogen ion concentration or the hydroxyl as required for each of the following, and state whether the solution is neutral, acidic, or basic. All right, so A has given to us a concentration of 1.0 times 10 to the minus 4 molar hydroxide. Right? If we put hydrogen ions times hydroxyls, 1.0 times 10 to the minus 4 equals 10 to the minus 14, then we divide this one by 0.4, right? 10 to the minus 4. That means this one is 10 to the minus 10 molar hydrogen ions. Okay? Compare 10 to the minus 4, 10 to the minus 10. Which one is greater? In this case, hydroxides greater than hydrogen ions. This is basic. All right? How about 2 molar hydrogen ions? So B would be 2 molar hydrogen ions. Right? If we go 10 to the minus 14 equals 2 molar times hydroxide, then we would divide this one by 2. So 10 to the minus 14 divided by 2 equals hydroxide. Okay, so we can factor that one out. That's equal to 1/2 times 10 to the minus 14, or 0.5 times 10 to the minus 14, or 5 times 10 to the minus 15 molar. That's the hydroxide concentration. All right, so in this case, the hydrogen ion concentration is greater than the hydroxide. This is acidic. Well, it's also greater than 10 to the minus 7, which would be neutral. All right, so either way, either interpretation gives us the correct answer. So an acidic solution is defined as an aqueous solution in which the concentration of hydronium ion is higher than the hydroxyl ion. That's true. Okay. I've got more time, so I'm going to go ahead with pH. What do we mean by pH? Well, there was a Danish chemist who was working with enzymes named Sorensen at the beginning of the 20th century. And I can only assume that he was weary from expressing acidity and basicity in terms of the hydrogen ion or the hydroxyl ion concentration. And they're always very small values, so you have to use scientific notation, and it gets to be a pain, right? So he understood mathematics enough that if he converted the values of hydrogen ion into a logarithm, then he would get a more compact value. So here's what he did. He took the hydrogen ion concentration, whatever it happened to be, take the log of it, right? That means base 10. Okay? So when he did that, for instance, if it was neutral, it would be 10 to the minus 7 molar. So what would the log of that be? Well, what does the logarithm mean? It means that this value, this number over here, is the power of 10, right? 10 to what power that gives you that number? In that case, it would be minus 7, right? Okay. Well, he didn't want negative numbers either. So he said, okay, let's put a negative in front. Now it's positive. And he called that pH. Small p, capital H. If you write it this way or this way, it is wrong. Okay, what we also notice is that when we have a scale here, right, neutral would be 10 to the minus 7th molar hydrogen ion. Okay, that would be neutral. If the concentration of hydrogen ions increase, right, so they could go up to maybe 10 to the minus 1 molar hydrogen ions. This pH would be 7. What would this one be? This one would be 1 pH. But it's a higher concentration of hydrogen ions, and this is acidic. This is the acidic side. So what do we know about this? Well, the more acidic is the lower pH. And we can go the other direction, the basic direction, where the hydrogen ion concentration decreases even further, say 10 to the minus 12 molar. And that would be a 12 pH. That would be basic. So the higher the pH value, the more basic it is. So why don't we calculate the pH for these possibilities here? The first one, 10 to the minus 4, hydrogen ions. 10 to the minus 4. Take the log of it and then change the sign, and that is 4 pH. Okay? Actually, it's a 4.0. Let's see. Oh, it's 1.0, two significant figures. That's right. It should be 0, 0. What I'm looking at here is how many significant figures are in that concentration. This is 1.0 times 10 to the minus 14. Two significant figures means 2 decimal places in the pH. All right, how about the next one? pH of the next one, 0.04 molar hydroxide. For this one, we need 10 to the minus 14 equals hydrogen ions times 0.040 molar hydroxide. So we'll divide this one into that one. Let's see, 1 times 10 to the minus 14 divided by 4 times 10 to the minus 2. Right? So that's 1/4 times 10 to the minus 12. This is 0.25, or 2.5 times 10 to the minus 1 times 10 to the minus 12, which is 2.5 times 10 to the minus 13. And then we take the log, the negative log of this, because this is the hydrogen ion concentration. Okay? And that should be 12.6 pH. And let's see, two significant figures. Let's see, I left this one out. This is 4.0 times 10 to the minus 2. Yeah, 2 decimals, 2 significant figures, 12.6 pH. Okay. All right. Erase this. Now, suppose we are given the pH of a solution. If it's pH 5.85, what's the hydrogen ion concentration in this solution? Well, this is equal to negative log of hydrogen ion concentration. So remember the definition of our logarithm. This would be the power of 10 that's equal to that, except we can't have that negative there. We got to move the negative over. So minus 5.85 equals the log of hydrogen ions. So now 10 to the minus 5.85 is equal to hydrogen ion concentration. All right. And that's 1.4 times 10 minus 6 molar. Let's see, 2 decimal places, 2 significant figures. We're good. All right, we've discussed this already. If the pH is 7, solution is neutral. pH is greater than 7, it's basic. pH less than 7, it's acidic. And that is for 24 degrees Celsius. If you change the temperature, you're going to change the K value. But as long as the hydrogen ion concentration and the hydroxyl ion concentration are equal, no matter what they are, at a different temperature, then you have a neutral solution. These are some examples. I'm going to skip those. There's the correct expression for pH, and it's a mathematical expression, just like the KWs and the KAs and the KEQs. It's math. So if you have all the variables have a value, except for one, you can solve for it. Okay. All right. So let's expand the definition of pH. Since it's a mathematical transformation and that's it, then we can also say, if we know the hydroxide ion concentration, we can take the negative log of that. That's going to give us POH. Okay? Or if we know the K value of, say, an acid, we take the negative log of that. That gives us pKa. All right? Or if we know what the Kw is for water, then the negative log of that is pKw. Now, if we know that Kw equals hydrogen ions, hydroxyl ions, and that value at 24 degrees is 1 times 10 to the minus 14, then if we take the negative log of everything inside that equation, what do we get? We get pKw equals negative log of this, pH. The log of A times B is equal to the log of A plus the log of B. So the log transformation of that, we have to add the log transformation of this one. Okay? And this one then would be 14. Like that. 2 significant figures, 2 decimal places. So this also simplifies calculations. If you're given the hydroxyl ion concentration and you want to know pH, just calculate POH and subtract it from 14, and that'll give you pH. Let's see, do we have that example here? All right, we have that one. Oh, okay. So the pKa for HF, given that the Ka for the acid is 6.8 times 10 to the minus 4. All right, so the negative log of 6.8 times 10 to the minus 4 would be the pKa of hydrofluoric acid, which is 3.17. Now notice what we said earlier. If the K value is large, and this is not particularly large, but it's better than some. Some of them are 10 to the minus 10, 10 to the minus 12, 10 to the minus 14. This one is large by comparison. Then we know that the reaction itself is to the left. It's unionized HF. But we also know that when we take the pKa of that value, that is 3.17. So the log transformation in this situation gives us a value. The larger the value here, the smaller the pK. Okay, pKa is another method of expressing strength of an acid. If the Ka of a solution is 6.3, what is the pKa, and is the solution acidic or basic? All right, the pK is acidic. Yeah. And we can look at that in terms of 3.20. The lower the value, the more acidic. If the pK were greater than 7, then it would be basic. Okay. So we talked about salts already. And what happens when you put a soluble salt into solution? Well, the cation and the anion separate from one another, and they are then surrounded by either hydroniums or hydroxide ions, or both. All right. So let's make some room. So if you have the salt of a strong acid and a strong base, we want to predict the pH or the acidity or basicity of the solution. If we have a salt from a strong acid or a strong base, what does that mean? Say you had this salt. What would be the base associated with this salt? Well, if we react KOH and HCl, then we get KCl plus water. That's what we mean. This is a strong base, this is a strong acid. When this salt goes into solution, it produces a neutral solution. Right? Strong acid, strong base produces a neutral solution if the salt is formed from a strong acid and a strong base. If in this example, right, what would this be formed from? This would be ammonium hydroxide plus hydrochloric acid. Right? That would produce the ammonium chloride plus water. All right, what's going to happen now? Well, this is a weak base, formed from a weak base. This is a strong acid. The solution is going to be acidic. All right? Now, one thing that I didn't mention earlier is if you have a strong acid like this, and it produces hydrogen ions plus chloride ions, if this is strong acid, this is weak base, conjugate base. What that means is when the chloride ion itself is in water, it doesn't want any protons. It will not take protons from anybody. It's a weak base. But if you have a weak acid, and in this case, ammonium is a weak acid, then when it reacts with water in solution, it transfers the proton, makes ammonia, and the hydronium ion. That's why this combination makes an acidic solution. It's chemically speaking, it's not because of the acid, it's because of the conjugate base. We have the conjugate acid of the base, right? This is the conjugate acid of that base, and it will react with water. If this is a weak base, this is a strong acid, relatively speaking. It transfers its proton over to water, and that makes the acidic condition. So the rule of thumb is, if the salt is formed from a strong acid and a weak base, you get an acidic solution. And conversely, if the salt is formed from a weak acid and a strong base, then the salt will produce a basic solution. So the weak acid is here. The weak acid is here, and it produces a strong base here. So that strong base wants protons badly, and it takes them from water. And when it does that, it produces hydroxyl. That's where the basic comes from. The basic doesn't come from the base, the strong base, it comes from the weak acid and the conjugate base of the weak acid. Now, when you have a weak acid and a weak base combined, it could be either acidic, neutral, or basic. And in order to determine that, you need to know the Ka of the acid and the Kb of the base and compare them. Which one is larger? The one that's larger wins, right? And this course is not suited for going into that much detail at this time. Just know that it depends on the Ka and the Kb of each component. Okay, some salts hydrolyze when placed in water. Let's see, when the salts of a strong acid, strong base are placed in water, the resulting will be neutral. All right, we got a few more minutes. Talk about buffers. What is a buffer? In terms of acids and bases, a buffer is an aqueous solution that once it reaches equilibrium, if you add a strong acid to it, the pH will only change very slightly. If you add a strong base to it, the pH will change only very slightly. A buffer resists the change in pH when you add either an acid or a base to it. Now, typically, a buffer system is composed of a weak acid and its conjugate base. Okay? That mixture will produce a buffer if they're in the correct concentrations. So if this is a weak acid, that means this is a strong base. And if we set up the equilibrium here like that, right? Aqueous, aqueous, aqueous. And we have some of this in solution and some of that in solution. By the way, how do you get that? Well, this is easy. You just add the acid. How do you get this one in there? You get this concentration in there by adding a soluble salt, right? Like sodium A or potassium A. And as it turns out, the best combination of concentrations for these two let's see, let me put it the other way. Put this one on top. The best combination there is 1, where they're exactly equal. That gives you the best buffer region. Okay, so what happens if this is a buffer solution? What happens when you add acid? Well, you're adding hydrogen ions. If you add hydrogen ions here, right, then you increase this one and you shift the equation that way. You shift the reaction to the left. That consumes some of this, but it also removes hydrogen ions, right? So the pH moves only slightly. How about hydroxyls? Well, hydroxyl is a very, very strong base. Why? Because it comes from a weak acid, water. So if you add hydroxyls, you can look at it 2 different ways, right? It can react with this hydrogen ion and produce water and shift the reaction this direction, right? And as it consumes, as the hydrogen ions react with this hydroxyl and produce water, the hydroxyls are taken out or removed to a large extent. Or you can put the hydroxyls over here, right? And that would produce water plus A minus, right? So the water goes into the solvent, and this one ends up over here. And it produces some hydrogen ions also. But still, the pH changes very little as a consequence. Okay, let's see. All right, we discussed that, adding a base. Okay, in this scenario, adding the base, the hydroxyl, combines with the hydrogen ions and makes water. And that shifts the reaction to the right. Adding acid reacts with the conjugate base, the A minus part. And that also shifts to the right. Excuse me. It shifts to the left, pardon me. Shifts to the left. All right. Now let's talk about this equation. This equation is especially useful. And it was developed in stages. The first stage was proposed by a scientist named Henderson. Henderson took this equation, HA yields H plus and A minus, and he said, okay, the equilibrium constant for this acid is H plus times A minus divided by HA. And then he solved for the hydrogen ion concentration. That's the Henderson equation right there. Ka times HA over A minus. Well, about the time that Henderson finished and proposed this transformation, Sorensen came up with the pH idea. So Hasselbalch took Henderson's equation and applied Sorensen's transformation. And the first step would give you the pH for the hydrogen ion concentrations, the pKa, and then the negative log of HA over A minus. Now, we're not going to call pHa over A. That doesn't make any sense. So we leave the negative log of HA over A minus alone. It just stays as a separate entity. But we want to get rid of that negative. So what we know about logarithms is that the negative log of A over B is the same as the positive log of B over A. So we just flip the A minus and the HA, and that changes the sign to positive. And that is the Henderson-Hasselbalch equation. I don't know if we have time or the need to go into a lot of detail. What we're saying is that if you have the concentration of the conjugate base, A minus, equal to the value of HA, then pH equals pKa plus the log of A minus over HA. What happens if these two are equal? If they're exactly equal, that's 1. So in terms of logarithms, what is the power of 10 that equals 1? X equals 0. So this whole term, when these are equal, this whole term becomes 0. And at that point, the pH is equal to the pKa. What that means is the ideal pH for any weak acid that we want to use is equal to its pKa. All right. So if we have a solution that's made up of 0.45 molar acetic acid and 0.85 molar sodium acetate, which means 0.85 molar acetate ion, the conjugate base, and the Ka is 1.8 times 10 to the minus 5, what is the pH of that buffer solution? Well, the concentration of the A minus and the HA are not the same in this case. So we have to use the Henderson-Hasselbalch and calculate it. Right? So there's our equation. And we substitute the values and we find that our pH is actually 5.02. All right. So we're nearing the end. We're talking about electrolytes. What is an electrolyte? Well, electrolyte is anything dissolved in water that makes the light come on. Electrolyte. What that means is when you dissolve an acid or a base or a salt in solution, what does it do? It breaks up in some form into ions. And if it breaks up into ions in solution, then when you have an electrode here, it goes around and there's a battery. And then there's a light bulb. Let's see here, like that. If this has ions in it, then the charge can be transferred from one electrode to another and complete the circuit. And in that case, the light bulb comes on. That's an electrolyte. It's an operational definition. Right? Here's an example. Well, here's an example of a non-electrolyte. If you put something in there that is dissolved, but it doesn't produce ions, you won't get the light bulb on, which means it's a non-electrolyte. Perfect example of that is table sugar. You can dissolve a ton of table sugar in a little bit of water, and it will never turn the light bulb on. Strong electrolytes make a bright bulb, which means the voltage is high. Actually, the current's high, excuse me. The current is high because you have lots of ions to transfer the current. Weak electrolyte would be a weak light because you have very few. And that would be like a weak acid, like acetic acid in low concentration will light the bulb very dimly. All right. Now, there's one more concept that we want to introduce when we're talking about acids and bases. It's known as the equivalent. And this works for equivalents of hydrogen ions, hydroxyl ions, or ions of any kind. So, if you have 1 mole of chloride ions, that is 1 equivalent of chloride ions because it only has a single charge. So there, in that case, it's 1 to 1. If you have a mole of sulfate ions, you have 2 equivalents of sulfate because it's doubly charged. So you're actually tracking the charges of the species. Phosphate would be 3 equivalents for every mole. Now, when you have hydrogen ions, say if you have sulfuric acid, right? If you have 1 mole of sulfuric acid, how many equivalents of hydrogen ion do you have? You have 2 equivalents of hydrogen ions that are possible. Okay, so 1 mole of sulfuric acid makes 2 equivalents. And the idea of a milliequivalent is just 1,000th of 10 to the minus third. We mentioned electrolytes. When you have blood work for your doctor and urinalysis, they will always include, nearly always, include electrolytes, right? What's your electrolyte balance? There are normal ranges, right? If you exceed those ranges, either below or above, then that's a sign of some pathology. And the electrolytes are going to be the charged species, right? We always have sodium, potassium, calcium, magnesium, and we also had chloride. We have bicarbonate. We have hydrogen phosphate ions. We have sulfate ions. All these things in our system. So if the concentration of calcium ion present in a sample is 5.3 milliequivalents per liter, how many milligrams of calcium ion are present in 180 milliliters of sample? This actually, once you understand the definition of the equivalent, this is actually a dimensional analysis problem. If you start out with 180 milliliters of that solution, we need to know what is, how many liters is that, right? So if you know the number of liters, right, then you can cancel liters with 5.3 milliequivalents per liter, which is its concentration, and change the milliequivalents to equivalents. And we know that 1 mole of calcium ions is equal to 2 equivalents. So now we can cancel the equivalents. And that will give us the moles of calcium ion. Now we can convert calcium ions into grams or milligrams, as the case may be. Right? And an ion of an element is essentially the same molar mass, right? Because electrons weigh like 1,800 times less than a proton, so they're really insignificant. And we find out that under those circumstances, you have in your possession 19 milligrams of calcium ions. Okay, while discussing mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. The concentration of ions is specified using the equivalent unit. That's one of the advantages of the equivalent. It allows you to compare apples and apples. In other words, we can compare potassium, calcium, aluminum, right, or other negatively charged ions in the same sentence, because when we say equivalence, that means that takes into account the molar concentration and the charge. So what's a titration? Well, it's an experiment that we don't have time to do in this course. But essentially what it does is an acid-base titration takes one solution for the concentration of which we know very accurately. It could be acid or base. And then the other one, the opposite, if it's acid then the base, the other one is an unknown concentration. And we titrate them. In other words, we put an unknown amount of the unknown concentration, and then we add dropwise the known concentration until we reach an equivalence point. And the equivalence is where the hydrogen ions and the hydroxyl ions are exactly equal. And at that point, we read the volume. We read the volume off of our acid. Let's say the acid is known and the base is not. So we have the molar concentration of the acid, and we know the volume of the acid, which means the moles of acid, right? From our definition of molarity. Well, the moles of acid should be equal to the moles of base, as long as they're 1-to-1, right? If they're not, then we could use the equivalence value for concentration. And I'll do that in just a second. This would be the molarity of the base times the volume of the base. Well, we know the volume of the base. Now we know the moles. We can solve for the molarity of the base. Now, if we're titrating a monoprotic and a monohydroxyl, monoprotic acid, monohydroxyl base, then this works. But if we've got, say, a monohydroxyl base and a diprotic acid, then the better concentration unit is what's called normality. And the normality is equivalence per liter. So when we do that, we've taken the charge or the protic nature of the acid and incorporated into this value. So the normality allows us to make this calculation. So we just need to know the equivalence divided by the liters, and we get the concentration. So for hydrochloric acid, 1 molar equals 1 normal. Right? For sulfuric acid, 0.5 molar equals 1 normal. Right? Because for every mole of this, you get twice as many moles of hydrogen. That means 2 equivalents. So 1 normal in this case. This is a device that we use. It's called a burette, and it's calibrated. The ones we have here are calibrated in tenths of a milliliter. Allows you to deliver an exact amount. They're marked from 0 at the top to ours has 50 at the bottom, 50 milliliters. The reason is you're starting at 0 or something high, and then you're delivering it, right? So if you start at 0 and you drop down to 10 mils, then you have delivered 10 milliliters. That's why the calibration is in reverse from a graduated cylinder. Now, the equivalence point is the point where hydrogen ions are exactly equal to hydroxyls. And it's difficult to do that if you have a large number of samples. So if you have 100 samples to do in one day, you need a quicker way to do it. You need an indicator. So the equivalence point will be this. The end point, this will be the equivalence point. The end point is as close as we can get to that value using a color indicator. So we get a color change when it's very close to that equivalence point. That's the difference between equivalence point and end point. So here we've added some of our titrant to the Erlenmeyer flask, and it changed colors. So we read the volume and move on to the next sample. Okay, if we titrate sulfuric acid and sodium hydroxide, how many moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid? Actually, 1 mole of hydrogen would react with 1 mole of hydroxide. Okay. In an acid-base titration, determining the concentration of an acid or a base, an acid-base titration is performed using an acid-base indicator, which changes colors near the desired pH. The pH at which this changes, this is equal, will depend upon the nature of the acid and the nature of the base. It's not always pH 7. So if a solution contains 9.34 times 10 to the minus 8 molar, has a pH of, just take the negative log of it. Right? So it's going to be 7 and essentially neutral. Right? We could say it's slightly basic, but that's not an option. And the hydroxide ion concentration is 7.3 subtracted from 14, and then use the anti-log of that value, of the negative of that value. Okay. I'm about out of time. So there's a calculation of a titration that gives us the concentration of the acid when we know the exact concentration of the base. Okay. So that's the end of that. Stop the share. And next week, we'll have time to devote entirely to the lab. osmosis and dialysis. We'll get to do pre-lab discussion and then have time to do the lab, because we won't have to deal with any more lecture.